Welcome to The Explainer. Today, we're diving deep into significant figures. And trust me, this is way more than just rounding numbers. It's the fundamental language of science, the way we talk about how precise our measurements really are. So let's kick things off with something you've probably seen a million times. You do a calculation, maybe divide two numbers, and your calculator just spits out this long string of digits. The big question is, how much of that is actually real? Which of those numbers actually mean something? Because here's the thing, just writing down that whole number is a huge mistake. It suggests your measurement was way more precise than it actually was. Significant figures are how we fix that. Okay, so here's our game plan. We'll start with the why, the language of measurement. Then we'll break down what makes a number certain or uncertain. After that, we'll get into the nitty-gritty rules for counting sig figs and using them in calculations. And we'll wrap it all up with a summary and some best practices to keep you on track. All right, let's jump into section 1, the language of measurement. I want you to think of significant figures as the grammar for scientific data. They're not just about the number itself. They tell a story about the quality and precision behind it. So, here's the absolute core definition you need to burn into your brain. Significant figures, or sig figs, are all the digits in a measurement that you know for sure, plus one. Just one that's estimated. It's that mix of the certain and the uncertain that gives a measurement its real power. And this is the key takeaway, right here. The more significant figures you have, the more precise your measurement is. Simple as that. A reading of 12.1 grams is not the same as 12.10 grams. That extra zero at the end, it's not just there for decoration. It's a statement. It's telling you something important about the tool you used. Okay, moving on to section 2. Let's build on that idea. We're going to dissect a measurement and look at its anatomy, the parts that are certain and the one part that's always a little bit uncertain. This is a perfect example. Look at the analog stopwatch. You can probably say with confidence that it's 14 seconds. The 1 is a sure thing, but that 4? You're kind of estimating between the ticks, right? Now look at the digital one. It gives you 14.1 seconds. Here, the 1 and the 4 are solid, they're certain. The final one is the estimated digit. See the difference? More sig figs means a more precise measurement. The digital stopwatch is just a better tool for this job. Let's try another one. Imagine an analytical balance in the lab gives you a reading of 12.453 grams. What is that number actually telling you? It's saying, hey, I am absolutely positive about the 12.45. That last digit, the 3, that's the instrument's best guess. So in total, this number has 5 significant figures, 4 that are certain and 1 that's uncertain. Okay, section 3, let's get down to business with the rules of counting. This is where the rubber meets the road. Now, any digit that isn't a 0 is always significant. That's the easy part. The real trick, and where almost everyone messes up, is figuring out what to do with the zeros. And this table breaks it down beautifully by giving each type of 0 a job. First, you've got captive zeros. These are the ones sandwiched between other non-zero digits, like in 1.003. They are always significant. Always. Then you have leading zeros, like in 0.013. These guys are never, ever significant. They're just placeholders, showing you where the decimal point lives. Now, trailing zeros, this is where it gets interesting. If they're after a decimal point, like in 1.7, they are absolutely significant. They were measured. But if they're at the end of a whole number with no decimal, like 43,100, well, that's where things get ambiguous. And that ambiguity leads us right to this problem. If I write down the number 100, what do I mean? Did I measure to the nearest 100, the nearest 10, or the nearest single unit? It's impossible to tell. It could have 1, 2, or 3 sig figs. And in science, that kind of ambiguity is just not acceptable. So what do we do about it? The solution, and it's a really elegant one, is scientific notation. It is the single best way to kill any and all ambiguity. If you write 1 times 10 to the second, you are shouting from the rooftops, this has one significant figure. But if you write 1.00 times 10 to the second, you're making it crystal clear that you have 3 sig figs. No guesswork neither. All right, section 4, rules for calculation. So now we know how to count sig figs. The next step is, how do we handle them when we start doing math? This is all about how uncertainty gets passed along or propagated through our calculations. But before we can do that, we need to agree on some rounding rules. The first 2 are probably what you learned in grade school. If the digit is bigger than 5, round up. If it's less than 5, you leave it alone. But what about step 3? what if the digit is exactly 5? This is where we use something called banker's rounding. You round to the nearest even digit. So 8.65 becomes 8.6, but 8.75 becomes 8.8. Now, why on earth do we do this? It's actually a clever statistical trick. Over a whole bunch of calculations, it prevents you from always rounding up and introducing a slight upward bias into your data. It's the most accurate way to do it. Okay, for adding and subtracting, the rule is surprisingly simple. Your answer can't be more precise than your least precise measurement. You just line up the decimal points, do the math, and then look at which number has the fewest digits after the decimal. In this case, 3.31 only has 2 decimal places, and that limits our whole calculation. Our final answer has to be rounded to 2 decimal places too. Now for multiplication and division, the rule is totally different. Don't mix these up. Here, it's not about decimal places. It's about the total number of sig figs. I like to think of it like a chain. Your final answer is only as strong as the weakest link in your calculation. So you look for the measurement with the fewest total significant figures, and that's what determines the sig figs in your answer. So let's go all the way back to that problem from the beginning. We're dividing 8.314, which has 4 sig figs, by 2.2, which has only 2. Our weakest link here is 2.2. It only has 2 sig figs. That means our final answer, no matter what the calculator says, must be rounded to 2 significant figures. So that long, crazy number becomes just 3.8. There is also a special rule for logarithms, which is super important in chemistry for things like pH calculations. The rule is this: the number of digits in the mantissa, that's the part after the decimal point in a logarithm, has to be the same as the number of sig figs in your original number. Let's look at an example. Say we take the log of 224. Now, 224 has 3 significant figures. The raw answer on a calculator is something like 2.3502 and so on, but our rule says we need 3 digits in the mantissa. The 2 before the decimal is called the characteristic. It just tells us the power of 10. The part we care about is the 0.350, the mantissa. Those 3 digits match the 3 sig figs in our original number, 224. So the correct answer is 2.350. Okay, let's bring this all home in our last section with a solid summary and some best practices. Think of this as your exam toolkit, everything you need to nail this stuff. This table is your cheat sheet. Seriously, memorize it. Addition and subtraction, it's all about the fewest decimal places. Multiplication and division, you're hunting for the fewest total significant figures. And for logarithms, the sig figs in the number become the digits in the mantissa. Got it? And finally, let's talk about the common traps people fall into. The number one mistake is mixing up the addition and multiplication rules. People also forget to count those captive zeros, or they mess up the banker's rounding for numbers ending in 5. And please, the cardinal sin of lab reports, never, ever just copy and paste the raw output from your calculator. Your answer has to mean something. So, why do we care so much about this? Because as the source material points out, in a field like analytical chemistry, this isn't just a suggestion, it's the law of the land. Reporting data with the correct number of significant figures is how you show you're a competent scientist. It proves you understand the story your numbers are telling. So I'll leave you with one last question to chew on. Now that you know the rules, which type of calculation is riskier? Where do you think you could lose more precision if you get it wrong? When you're adding numbers or when you're multiplying them? Something to think about. Thanks for tuning in.